All right, let's jump right into it. Welcome to this rapid-fire, high-yield explainer on GI physiology and pathology. If you're prepping for your foundational block exams or, gearing up for Step 1 or COMLEX, you are in the exact right spot. We're going to strip away the fluff and focus purely on the facts and frameworks you need to rack up those points. Let's build that solid foundation so you can crush those tricky board vignettes with total confidence.
So here's our roadmap for the review. 1. Cellular transport mechanisms. 2. Lipid pathways. 3. Regional absorption sites. 4. The digestive sequence. And 5. Clinical pathology. Let's get to it.
Section 1. Cellular transport mechanisms. Let's dive straight into how the end products of digestion actually manage to cross the intestinal mucosa.
Right off the bat, a super high-yield distinction is separating passive from active transport. You probably know this, but passive transport relies entirely on a concentration gradient. It moves stuff from high to low without burning a single drop of ATP. It's literally like rolling a boulder down a hill. Active transport, on the flip side, takes work. It spends energy to forcefully shove substances against their natural gradient, from low to high. A classic board example, the sodium-potassium ATPase pump. It just constantly churns through ATP to keep those electrochemical gradients intact, which, as we'll see, is absolutely vital for absorbing other nutrients. Now, don't sleep on facilitated transport on test day. It's kind of this interesting middle ground. Just like passive transport, it doesn't cost any energy and moves from a high to a low concentration. But, and here's the kicker, it uses specialized protein channels to do it. Think of them as biological doorways. A perfect clinical example is the GLUT family of transporters. They simply open the door for glucose when there's plenty of it floating around outside the cell.
All right, time for a quick active recall prompt. Put your test-taking hat on for a second. Based on what we just reviewed, which essential nutrients are versatile enough to use all three mechanisms: passive, facilitated, and active transport? Take a guess.
Walk this one in. The answer is both glucose and amino acids. These guys are metabolic VIPs, so they can be absorbed passively, actively, or via facilitated transport depending on exactly what the body needs. For instance, glucose uses secondary active transport through the SGLT1 transporter on the luminal side, basically piggybacking on sodium to drag itself in against the gradient. Then, it hops into the bloodstream via facilitated diffusion using GLUT2 on the basolateral side. That right there is textbook high-yield board material. Oh, and as a quick bonus fact, remember ions are a bit more rigid. Chloride mostly goes passive, while sodium overwhelmingly relies on active transport. And hey, we can't talk transport without mentioning water. Water absorption is straight-up osmosis. It just flows from high water concentration to low water concentration through a semi-permeable membrane that only lets the tiny particles pass through. Clinically, this osmotic gradient is exactly what gets wrecked in secretory diarrheas. Think cholera. Massive chloride secretion dumps into the gut lumen, water aggressively follows it osmotically, and suddenly you've got severe, life-threatening dehydration.
Moving right along to Section 2, Lipid Absorption Pathways.
So lipids, they just don't play by the same rules as our water-soluble nutrients. They have their own mucosal barrier pathway, and this sequence is incredibly testable. Let's break it down. Step 1, we start with fatty acids and glycerol. Because they hate water, they can't just float across the intestinal lumen. So step 2, bile salts from the liver step in to emulsify these fats into tiny soluble droplets called micelles. That micelle formation is crucial for getting the lipids up close to the brush border. Step 3, they enter the cell and get packaged up into chylomicrons, complete with a specialized protein coat. And step 4 is the big twist. Instead of doing straight into the bloodstream and hitting the portal vein like glucose does, these bulky chylomicrons totally bypass the initial blood vasculature. They get absorbed directly into the lacteals, the lymphatic vessels of the intestine, and eventually dump into the venous system via the thoracic duct.
Section 3. Regional absorption sites. Time to zoom out to gross anatomy.
Let's picture a nutrient traveling down the tract and see what gets absorbed where. Starting at the mouth, overall nutrient absorption is basically zero, but it's super relevant for certain drugs, like sublingual nitroglycerin, which hits those mucosal capillaries for a rapid systemic effect. Down in the stomach, the acidic environment handles water, simple sugars, and alcohol. But look at the small intestine. This is where the real magic happens. Massive, sweeping uptake of glucose, fructose, fatty acids, glycerol, and amino acids. Finally, whatever's left over hits the large intestine, which just scavenges the remaining water, a few minerals, and specific drugs.
If you take away one thing from this regional map, it's this. The small intestine is the undisputed MVP for nutrient absorption. It's also where final chemical digestion actually finishes. Why is it so good at this? Because its anatomy is just insane. The circular folds, villi, and those dense microvilli forming the brush border massively increase the surface area. It's basically a giant nutrient trap. Honestly, the rest of the GI tract is just playing a supporting role to what happens in the small intestine.
Section 4. The Digestive Sequence. Let's put this all into a physiologic timeline. It flows perfectly in 4 stages. Step 1. Digestion. This chemical and mechanical breakdown officially wraps up in the duodenum. Step 2. Absorption, which, like we just said, peaks in the small intestine. Step 3 is assimilation. This isn't just some textbook concept. This is where your patient's tissues actually grab those substances to build cells, fix damage, and crank out daily ATP. And finally, step 4, defecation, the voluntary removal of indigestible waste driven by massive peristaltic movements in the colon. Section 5. Common digestive system disorders.
All right, let's bring all this physiology into the clinic and see what happens when things go wrong. Starting broad, one of the most common things you'll see on the wards is general intestinal inflammation, usually from a foreign invader. Think of your classic viral gastroenteritis from norovirus or a bacterial infection. These bugs directly attack that delicate mucosal barrier we talked about earlier, causing widespread inflammation, crazy fluid shifts, and just a totally miserable patient.
Now picture this vignette. A patient walks into your clinic with distinctly yellow skin and yellowing of the sclera in their eyes. This is jaundice. Basically, this is a clinical flashing light for hyperbilirubinemia. It means there's a fundamental failure in the liver or biliary tree and bile pigments are being deposited systemically right into the patient's tissues.
What about vomiting? The high-yield takeaway here is the neuroconnection. The forceful ejection of stomach contents isn't just some local GI glitch, it is centrally controlled by the vomit center in the medulla of the hindbrain. For the boards, remember the area postrema, which houses the chemoreceptor trigger zone, or CTZ. Because the CTZ actually sits outside the blood-brain barrier, it can freely detect emetic toxins in the blood, kicking off that vomiting cascade, which is almost always preceded by a severe wave of nausea.
We've also got to contrast our 2 major motility extremes. Diarrhea is an issue of excessive frequency and crazy high fecal liquidity. This is dangerous, guys, because it shuts down food and water absorption. Clinically, severe diarrhea causes massive volume loss, leading directly to profound hypokalemia and non-anion gap metabolic acidosis. If unmanaged, that is absolutely life-threatening. On the flip side, constipation is a retention problem. Waste sits in the colon way too long, pulling too much water out, leaving hardened stool and causing highly irregular, really painful bowel movements.
Finally, there's indigestion, or clinically dyspepsia. Your patient will describe this really uncomfortable feeling of fullness, like their food just isn't digesting. It's often due to inadequate or uncoordinated enzyme release. The triggers? Well, they're everywhere. It could be acute stress from mild food poisoning or just everyday lifestyle factors like psychological stress, chronic overeating, or crushing way too much spicy food.
To wrap up this explainer, I want to leave you with a synthesis question to tie all this together. If a patient presents with severe liver dysfunction, kind of like that jaundice case we saw, and they have dramatically inadequate bile production, how does that clinically disrupt the lipid absorption pathway we mapped out earlier? Which specific lipid transport structures would fail to form first? Think back to that micelle step and how solubility dictates absorption. Ponder that before your next exam. Keep grinding, and I'll see you in the next one.